All right, didn't get any emails for questions this morning, so I've got the chat open in case you got any questions. Again, these are not lessons, these are not lectures, these are office hours. If you have a question, post in the chat. Remember, there's about a minute lag between me seeing it and responding, so you're just going to have to give it a minute. But I am here getting work done. All right, so I got a question about how we determine between SN1, SN2, E1, E2 occurring any type of reactions given. So your 1 versus 2 mechanism is going to be set more by the solvent than it is by the reagent. So whether it's unimolecular or bimolecular, substitution versus elimination depends on how basic the nucleophile is. So, wow, this looks like it's tilted. So what you kind of get is a spectrum. So if we wanted to decide between unimolecular and bimolecular, so 1 versus 2. If we want to get a bimolecular elimination or substitution, what we're looking at are nonpolar solvents, aprotic, and a low dielectric constant. And you can find the dielectric constants on, if you go to course material under lessons, there's a table of dielectric constants, should be at the top of the lessons menu. If we want to go to unimolecular mechanism, what we're looking for are polar, protic solvents, and generally these are going to have high dielectric constants to go with them. What the dielectric constant here describes is how well it can stabilize charges. So if it's something that's very bad at stabilizing charges, we're not going to create that carbocation that we expect to see for unimolecular reactions. If we have a high dielectric constant, that's going to favor it. Now, in terms of it doing elimination versus substitution. For it to do substitution, it needs to be small, fairly non-basic, but we can definitely have bases. The cutoff here is going to be hydroxide. A hydroxide can do substitution or elimination depending on how you drive the conditions. But generally speaking, hydroxide is going to kind of represent the tipping point. For us, we're going to consider it substitution, but you can definitely find plenty of examples where hydroxide is used for elimination. But we need to be small and fairly non-basic. Your extremes here, chloride, bromide, iodide, these prefer to do substitutions because they are not basic in the least. Weak acids, cyanides, things like that will fall on this spectrum. On the other end, to get the elimination, we need large, very basic groups. And so these are going to be your tert-butoxides, your isopropoxides, and to some extent you also get your ethoxides and methoxides, but they're going to kind of represent this other extreme where you're starting to get to that tipping point where they can do substitution just as well as they can do elimination. So here we have SN1, SN2, E1, E2. So if we've got a big bulky base and it's in a fairly nonpolar solvent, we're going to get an E2 elimination. If we're with a bulky solvent and we're doing a fairly protic solvent, this is going to give us more of an E1 elimination. Kind of the borderline here, sulfuric acid catalyzed dehydrations, H2SO4, on alcohols are going to kind of sit on the bottom end of this. To get our substitutions, we're looking usually at small non-basic molecules, chlorides, bromides, iodides, just substitutions, things that like to do substitutions. If we wanted to go through an SN1 mechanism, we'll put it in a polar solvent, particularly if we have alcohols. Alcohols really like to go through SN1 mechanisms. But if we start throwing in non-polar solvents like dimethyl ether, diethyl ether, things that really do not have any polarity to them at all, this is where we're going to drive the SN2 mechanism. Now, the reason why I'm presenting it purity as a spectrum is that it is a spectrum. There is no such thing as a purely SN1, SN2, E1, E2 mechanism. When we run these reactions practically in the lab, we do end up, if we're trying to go for SN1, we do occasionally get SN2, E1, E2. We just try to favor ourselves in which direction we want to go. So if we really want to drive elimination reactions, it's a Le Chatelier's principal method. These are all reversible reactions. Generally speaking, they're reversible reactions. And so we try to eliminate the product of the mechanism we're interested in. So if we're trying to do a substitution, we would try to eliminate the substitution product to drive that forward reaction. If we're trying to drive the elimination mechanism, we would work with something that would eliminate the product we'd expect from the elimination mechanism. Give you an example of showing how to use that. So let's say we wanted to do, let's say we had this molecule. So we have a bromo group and we want to favor substitution versus elimination, and we want to drive it by E1, E2. So if we want to do the substitution reaction, and we would need something to, because we're going to just react this with X negative. If we want to do a substitution, X here is going to be something like chloride, iodide, hydroxide, something small that's very easy to get in here and replace it. It's not likely to be sterically hindered in terms of doing a substitution. If we want to do it by an SN1 mechanism, we'd run it in like water. So we'd have hydroxide in water and we'd boil it, and that would drive, because we have a high hydroxide concentration, that would get rid of the bromine and give us the cyclohexanol. If we want to go by the SN2 mechanism, we're probably reacting into something like diethyl ether, methyl ethyl ketone, components like that. Now, SN1, SN2, this can give you carbocation rearrangement. This is going to give you a racemic mixture. We don't have chirality with this one. But for the SN2 mechanism, we ensure that we we invert the symmetry when we do the substitution. So if we want substitution, something small, SN2, something polar protic, or SN1, we want something polar protic, if we want to do SN2, something apolar aprotic. If we go over here to elimination, make sure you can see it. So elimination here, the solvent changes, but the reagents don't. So with elimination, our reagent changes. So on this side, if we want to do elimination, X here is going to have to be something big. And the ubiquitous example here is tert-butoxide or isopropoxide. And what these are going to do for us is they're very big. And because they're very big, they don't like to substitute. They can't get in there and push the bromine out. So what they do instead is they like to take hydrogens off of adjacent carbons because they're very, very basic molecules. So these are much better bases than hydroxide. Hydroxide can exist in water. These can't exist in water because they're so basic they actually pull the hydrogens right off of water. In fact, in any type of polar solvent or protic solvent, these are typically going to react with it. So if we want to drive like an E1 mechanism, we want the option of creating a carbocation, we would work with something like a tert-butanol or an isopropanol solvent so that our solvent and our reagent are kind of the same thing. But what this protonation is going to do is occupy these bases so we have time for the bromide to pop off. If we want to go by an E2 mechanism, we're going to work with, again, our ether and our ketone here. These are both very nonpolar. They're not going to be able to react. Smaller bulky is literally just the size of the molecule. So look at it in terms of total atomic weight. If we want to do a substitution, we're talking about methanol or smaller. So CH3OH or smaller will do substitutions. If we want to do eliminations, we're talking like big tert-butyl groups, isopropyl groups. You need a lot of carbon branching. And again, the idea here is just physical space. Something like the tert-butyl group, we talked about it with the axial equatorial positions, they're just big. They like to push things around because they have a carbon with 3 large CH3 groups, and those CH3 groups have 3 hydrogens sticking off the end. So they take up a lot of space. And there are definitely nuances with this, like is normal propanol, so like 3 carbons and an OH of the group, is that considered bulky? That's kind of a gray area with that when you're probably looking at a trade-off between substitution and elimination, but we're not going to deal with like really nuanced examples. If you have single atoms or 2 atoms, those are small. If you got, in this case, like 10 or 15 atoms, you're probably talking about a big bulky group. And with all things inorganic, you'll definitely find exceptions to this. Yeah, you're welcome. So yeah, 1 versus 2, this is solvent. This is whatever X is, whatever your nucleophile is. Yes, NH2 minus is definitely small. It's super basic, and we'll talk about when we get to alkynes. NH2 can also be used for elimination purposes, but it depends on the solvent of choice. So yeah, I would say NH2 can be used for substitution, but again, we'll talk about down the road how it can also be used for elimination. I learned the whole determination of the reaction wrong previously. I'm not quite sure what you mean there. Yeah, that was interesting. I was a little curious what that link was. Fortunately, it was pretty innocuous. I mean, I definitely got emailed far worse. I assure you, Peyton was lost without you yesterday. Yes, the virtual lab. Thank you for reminding me. Let's take a look at that. It's been a busy morning. Wait, you saw it, but okay, I think I know what's going on. Course tools, soft chalk. All right, check it now. I think what happened was I didn't synchronize the software. Soft chalk's kind of buggy that you don't really transfer it from one program to another. Yeah, I think the issue is that it's content that's copied over from a different core shell, and I think it's trying to get you to log in because it's trying to log into it's trying to get you to log into that other shell, which you don't have access to. Yes, that separation lab is actually one of their better labs for teaching techniques. Hmm. All right. Okay. Yeah, it was just a syncing issue. Again, it was just copied from a different core shell, and so it was trying to get you to log into that core shell. Hey, you're welcome. All right, I'll turn the camera back off. I don't think y'all really want to listen to me type. So online, it looked to see if substrate is primary or secondary, and from there they classify the reactions S and 1. So this is kind of a weird thing about reactions. So primary, secondary, tertiary. And there's the methyl version. We'll ignore the methyl version. So if you look at the rate of reaction, SN1 versus SN2. SN1 speeds up between primary, secondary, and tertiary. And SN2 slows down as you go from primary, secondary, and tertiary. So the thing that kind of gets missed in this discourse online is that you'll get a blend of both methods. So if you're looking at a primary substitution reaction, a majority of it is going to be through SN2, because that's the reason the SN2 mechanism was designed, was to explain how a primary carbon is capable of going through substitution. Because the original thought was it always has to go through carbocation. And it was like, well, primary carbocation is super unstable. Why would it do that? Well, there must be another mechanism. That's where the SN2 comes in. And then on the other extreme, if you have a tertiary carbon you're substituting, it's predominantly going to go through an SN1 mechanism, because that's faster. Because what we're doing is we're adding the rates of the SN1 and the SN2 to get the overall reaction rate. So generally speaking, when we're working with the tertiary, the fastest rate of reaction, it's not drawn here well, but your SN1 mechanisms are substantially faster than SN2 when they happen, because they are unimolecular mechanisms. Bimolecular mechanisms, because of how they work, are inherently slower. But the majority of the contribution of the rate for a primary carbon is going to be from the SN1 reaction SN2 mechanisms. But there is still some SN1 goes on, it's just a small amount. Whereas for tertiary, your predominant mechanism here is going to be SN1, and your SN2 is pretty much going to be a rare occurrence. Secondary is where it gets kind of dicey. They're probably both happening. So if you have a secondary problem, you're probably getting SN1 and SN2. But this assumes all things being equal, meaning that we're reacting first, secondary, and tertiary with the exact same solvent system with the exact same reagent. So there's actually a third dimension to that diagram I drew you, which is primary, secondary, and tertiary. Tertiary is going to lean much more towards bimolecular mechanisms. Primary is going to lean a lot more towards primary SN1 unimolecular mechanisms. No, wait, got that backwards. Tertiary is going to lean hard towards unimolecular mechanisms, whereas primary is going to lean heavily towards tertiary. So if you take that diagram I drew before, so we've got the nucleophile, we've got the solvent, and then a third axis here is going to be the carbon itself. And so, yeah, you can even get that. It's all both happening for that. So really, you're going to get this full three-dimensional diagram. So if you don't know anything about what's being substituted, use that diagram. And generally speaking, we don't try to do substitutions on primaries anyway. The big reason we don't want to do substitutions on primary is they're just very hard to react. Either they're going to be prohibitively slow, which is your SN2 mechanism. They're going to be super slow and super not practical, or you're going to have to drive the SN2 mechanism, which is practically faster, but lends itself to carbocation rearrangement. In fact, you've got an example of that in the packets where you've got this primary alcohol that you're subbing off. And you can take sodium chloride and you can reflux this over ether, and you will definitely get the SN2 pathway. This is something that definitely happens. But the thing is, you're going to be refluxing this for hours to make this happen. You're just not going to get, this is going to be a prohibitively slow process. Now, we can also do it with HCl and water. And in doing so, we'll end up getting this as our product. We'll form a carbocation, we'll get the methyl shift, and then we'll get a tertiary chloride. This will go super fast. You can probably do this in an hour and it will work just fine. But now you're going through an SN2 pathway. So it's really a matter of what you want to do. But I would say, again, if you don't know anything about what you're substituting, you're just asked SN1, SN2, E1, E2, do that diagram. Recognize that when you do get carbons, there's also the added effect that primary carbons much prefer the SN2 pathway, but the SN1 is faster. And tertiaries prefer the SN1. They're almost never going to do the SN2 simply because they're too bulky to engage in the SN2 mechanism. But the SN1 mechanism is practically faster, and it more just kind of hurts us in terms of stereoselectivity. Again, we can drive any substituted carbon to go through SN1, SN2, SN3. The question is, or I'm sorry, SN1 versus SN2. The question is, what's the ratio of SN1 to SN2? And this is where our solvent and nucleophile effect starts showing up, that our solvent can definitely really favor an SN2 pathway or really favor an SN1 pathway. This is actually something I highly criticize most organic chemistry textbook for, is that they do kind of oversimplify it. No, so for that one, you're going to ignore primary and secondary and tertiary. Again, I'm drawing it as a spectrum because reality, all four can be happening at the same time. The question is which way you favor it. But I would say if you do know something about the carbon, you can sit back and say, okay, if it's a primary, I probably am doing SN2. Like, even though I'm sitting in what's most likely an SN1 pathway, SN2 is probably dominating for a primary. For a tertiary, even though you may be seeing in an SN1 pathway, probably what's really going on is an SN2. But it's a practical consideration. I mean, organic chemistry, what I like about it is that it's the first time you actually deal with side products. Gen Chem, you never have to worry about side products. It's all straightforward reactions, like A plus B goes to C plus D. Here, this is why you have the purification steps. This is why you go to lab and learn how to use a SEP funnel, how to use a TLC. It's because you can get all these weird reactions. So a few weeks ago when we did the separations lab, we worked with sodium hydroxide. And we as instructors want to work with sodium hydroxide because carbonate bubbles when you acidify it. And so we were having a lot of issues with the carbonate basically bubbling out of the flask. You're welcome. So we were like, we'll switch to sodium hydroxide. This is great. And what ended up happening was it decomposed our acetyl salicylic acid. And so just switching our base, exact same reaction conditions, decomposed a reagent. And so this week we got to work with bicarbonate, which worked. But anyone who took the lab can tell you, once you start adding that HCl to bicarbonate, it just foams and boils. So just this little nuance of switching between sodium hydroxide at a pH of 13 and bicarbonate at a pH of 13, one decomposes acetyl salicylic acid, the other does not. Oh, most definitely. We're actually right now. It's looking like the tentative schedule in the spring is going to be in person for lectures. So half capacities, 8 people per section, but we are going to have seated lectures, which for me is going to be weird because I've never taught Organic 2 in person, so I have no idea what the pace of the course is. And for Organic 1, I've only taught it in person once. The nice thing about exams is like we can definitely dial in the exam. So like it's a really obvious example. This is going to go through SN1, SN2, E1, E2. It's really obvious what's going on. But you know, in real life, particularly with lab development, there's a lot of behind the scenes of we go run this reaction like 20 times trying to tune it in, which is fun. I mean, I'm not gonna lie, like it is kind of fun to go to the lab and screw around with this stuff. But right now, I'm trying to work on an oxidation reduction lab, and the reduction works perfectly. Like it doesn't matter what I'm doing; the reduction conditions are perfect. It's the oxidation conditions I can't get to work out. And I've tried primary, secondary, tertiary alcohols. I've tried things that I know naturally oxidize themselves and they still don't work with the reagent we're working with. Now we're having to switch to a different oxidizer to see if maybe that will work. But it's weird because the reactions are very simple. What we're trying to do is we're trying to take benzaldehyde, which is almond extract, and we want students to convert this to benzoyl alcohol, which is pretty benign. And we can test for both. Like this will react with, there's a reagent that works really well with this, and there's a reagent that works really well with this, so we can prove which one's there. But this direction's super easy. It's sodium borohydride, and the conditions work out perfectly, and you can smell it. You get rid of that almond smell, and you definitely produce the benzoyl alcohol. Can we go through bulky and smell more? Still telling which one's more bulky or smaller. What's the best way to do that again? So I would say count the atoms. So it's small if you've got 1, 2, or 3 atoms in the molecule. So something like chloride, iodide, bromide, hydroxide, these are all small. Teeny tiny atom, just single atom groups. The biggest I would say you could get to is methoxide. That's 4 atoms. So methoxide will probably do substitution more than it does elimination. If you get bigger than methoxide, and I mean like much bigger, so we're talking 10, 12, 15, 20 atoms, tert butoxide is the big example. So 4, 8, 12, 13, 14 atoms with this one. Isopropoxide, 1, 2, 3, 9 atoms. This is where you're starting to get into, it's more bulky than it is small, and it's definitely doing substitution. So for those examples, if you're referring specifically to the package, you'll notice all the solvents are the same, and that's the idea, is that it's kind of getting you to work along an axis. So that's where the nucleophilic effect on a reaction is saying is that, okay, all things are equal here. We're all working with the same solvent. Now, what do you expect this nucleophile to do in general? Versus there's another one where it's all the same nucleophile, but you're changing the solvent, and it's to kind of get you to think about that solvent effect. So it's getting you to sweep either axis. So yeah, that's kind of what it's doing, is like, okay, we'll keep one variable constant. What happens is you switch basicity. Okay, we'll keep the basicity constant. What happens is you change the solvent. Generally speaking, your nucleophiles are all going to be negative. There are exceptions. Nucleophiles are never positive, because the nucleophile has to like positive. And you're going to assume with all the examples you're given that a reaction does occur. There are exceptions to nucleophiles being negative, and these are ones that contain lone pairs. So oxygen and nitrogen can be nucleophiles on their own. But generally speaking, your nucleophile is going to be negative. So a nucleophile means positive loving, negative loves positive. Again, there are nitrogen and oxygen lone pairs can also act as nucleophiles. We'll talk about those reactions as we get further into the course. But you would never have a cation being a nucleophile, because the cation is positive. So there's no reason for a positive to want something that's positive. Yeah, you can definitely have neutral nucleophiles, but these are generally going to be nucleophiles that react through their lone pairs. So again, the oxygen and nitrogen are going to be the big ones that do this. Those nucleophiles tend to be weaker nucleophiles, but they do act as nucleophiles. So the homework's going to ask you to state the leaving group, but you don't need to state the leaving group. I'm not as worried about the leaving groups, particularly because some reactions get really complicated as to what the actual leaving group is. But generally, we're more focused on the organic compound anyway. So for me personally, I tend to focus more on like what happened to the organic molecule. You are correct in that there is, reaction should be balanced and you should write what happens. And again, the Connect homework does force you to do that. I'm just not so worried about it. Yeah, I just don't see a need to like focus on that aspect of it. Yeah, that's kind of my view, is that the most important is the major product. Because whatever that side product, whatever that second product is, we typically remove it off anyway. Yeah, you're welcome. So what ends up happening, yeah, there's some weird ones. So we'll get to polymerization next. That's more of a Orgo 2 concept. So we also kind of have to make the distinction here that there are acid and base catalyzed reactions as well. And we've got to stick to that argument whether it makes sense or not. So we can ask something like this where we have H3O plus and we have the alcohol group grab the OH2 group, form the OH2. But the thing is that we're calling this an acid catalyzed reaction, and that is technically true. So when we finish, we need to explain how we got our acid back. And this is where you'll see the leaving groups suddenly act as a base. Is because we did claim that the H3O plus here was in fact the acid catalyst, and by definition the catalyst can't be consumed. So for convenience, you'll see this written that, oh, the leaving group will suddenly become a really good nucleophile and pop it off. And this kind of contradicts our statement here that, well, if it's doing elimination, it should be big and bulky. The worst offender for this is when we see things like bromide and chloride being used as bases in these reaction mechanisms. That doesn't happen. But we need to explain how this is an acid or base catalyzed reaction, and so we kind of use the leaving group as the, it's kind of what brings the catalyst back into existence. So generally speaking, the common speaking here is due to the solvent. That's actually probably a much more likely explanation. So let's say you're running this reaction like methanol, so MEOH. Most likely the water is not what's grabbing your H plus off of this to make the alkene. It's probably your solvent because it's in such higher concentrations than your leaving group. But honestly, it doesn't affect anything. We just need a nucleophile to pull off that hydrogen and act as a nucleophile. And again, this is another reason why I'm not so worried about what pops off the right side. The devil's in the details in terms of like what happens to that hydrogen that gets extracted. But yeah, for a short answer, like it's just kind of there to like close the loop on why something's a catalyst and how that catalyst gets recovered. So Enol Polymerization. So, I mean, if you know the phrase Enol, this is the alternation between an alcohol attached to double bond and your ketone. And this is typically going to be mediated by some type of nucleophile. So the hydrogen is basically going to bounce back and forth between the nucleophile and the double bonds. So how do we occurs? So let me ask you a question, answer the question about the nucleophiles really quick. So neutral versus negative nucleophiles. And this is the thing that totally happens. So let's say I have chloride and I add ammonia. And we can definitely get this overall reaction where we substitute the chlorine off and we get the amine. Like, this is not impossible, but the question here is, why does this occur? Well, this occurs because we have a lone pair. So this is our nucleophile. These lone pairs here are negative, and they like the positive of that carbon attached to the chloride. So what we'll get is the nitrogen attacking the carbon and breaking the chlorine. And our first step in our mechanism is that we produce this is what I mean by we're going to get into some like really weird, doesn't make sense scenarios. So our leaving group here is our chloride, and what you'll see books write is that the chloride attacks the hydrogen and returns the lone pairs back to the nitrogen. Now, what's really happening here is that if ammonia is your solvent, your ammonia is going to use those same lone pairs to pull a hydrogen off that amine group and get you back to this. But this is a nucleophile too, and it doesn't take a negative charge. You can get what's called salvolysis. So salvolysis is where we have the solvent, in this case methanol, substituting off our chloride here to give us an ether. And again, this is going to work the same way. We've got a lone pair on the oxygen. These lone pairs are attacking the chloride, or attacking the carbon, displacing our chlorine to give us this species. And most likely it's not the chlorine that pulls the hydrogen back off. It's probably another methanol molecule that pulls that hydrogen off, and we just start acidifying the solution. In general, you don't, but the thing to keep in mind is that if you're looking for something like, well, it's base strength. So let's say we have a base, and in general, your base is going to attack the hydrogen to give you this reaction. Well, a neutral molecule is not that attracted to an H plus molecule, but definitely an anion is very attracted to a cation. So in terms of base strength, your neutral nucleophiles are not very good bases. They're more likely to do substitution than elimination, but you can definitely find examples where people claim these are doing elimination. This is going to be more of your substitution versus elimination. So this is going to do substitution elimination. This is going to favor substitution a lot more. These are both nucleophiles because they're both attracted to your positive charges, but if you want something that will do elimination, you definitely have to be working with an anion because they need that type of negative charge to really abstract the hydrogen. All right, polymerization. I'll do that really quick. So our polymerization here is going to be mediated by some intermediate nucleophile, so we definitely need something, preferably an anion, to make this happen. So how do we stimulate stability? So by itself, enols are not stable. So if we just have a straight enol, these are not going to be very stable because you have to work out the molecular orbital theory, but generally speaking, they're just not more stable. If we have a conjugated, that's a different story. So if we have our enol and we start conjugating it, this actually ends up being more stable than just the associated enol. Because in order to get to the ketone form, we have to break the conjugation, and there is a lot of stability associated with conjugation. Not all negatives favor elimination. It depends on their size. Smaller negatives are going to favor substitution, but definitely big, bulky negatives, those are purely an elimination. So terp-butoxides, isopropoxides, huge negative bases definitely only want to do elimination. Now, there's a special case where we have aromaticity. So an aromatic enol. So in this case, you're going to basically see a majority of this, but you're going to see an appreciable amount of the ketone, or the aldehyde in this case. For the aromatic enol, phenol is the big example. So with the aromatic enols, the ketone form does not, aldehyde ketone form does not exist at all. It will look like it. You can definitely draw reaction mechanisms where it is. But generally speaking, if you have to break the aromaticity of a ring in order to make your ketone, it's just not going to do it. But yeah, those are your three conditions. An enol itself is not stable. It does exist. If you create a conjugated enol, you're going to see a lot more of the enol form, especially as that conjugation gets bigger. But if it's aromatic, 100%, it's going to take the enol form. It's more just shorthand. So we know so when we originally had just the alkanes, so we'll just draw some generic alkane cyclic ring, we had to specify which one was where, because it's not clear looking at this drawing who number one is. But with the alcohols on a ring, we don't have to specify because we know alcohols get priority. So to say one cyclohexanol, any alkane, any alcoholic, or any alcohol on a ring, we automatically know the alcohol is in the first position. And so we don't bother listing it because it's just implied. So whatever functional group takes priority in rings, that's the number one carbon. So it's just kind of a waste of time to like write this extra information out, because if you wrote out every single ring that contained an alcohol with alkanes, they would all have one cyclo whatever the ring was. So we just leave it off. It's worthless information. And this will be true like when we get to ketones. Like if you've got a ketone group on the ring, so you've got a double bonded oxygen, we don't bother to give the position of the ketone because we know that's the number one position. There's nothing else, because it has such a high priority. We just know that's the number one carbon. I've seen the other. Now, this may also be a weird one where there's conflict in the naming. Organic naming isn't perfect, so I should probably go check your comment. But I'm pretty sure Carrie says like you're not supposed to bother naming the first one. Now, if the alcohol isn't the highest priority group, then yes, you do need to name it. So like they're usually named hydroxy. So the ketone I have there would be like 1-hydroxy cyclohexanone. All right, you're welcome. All right, so that's it. I actually need to prepare for a meeting this afternoon, so thanks you all for showing up. Again, if you ever have questions, please feel free to email them in advance or come to the live streams. And I will see you on Monday.